Hello everyone, welcome to this tutorial. I am Mathieu from Evolute, and today I'll talk to you about our latest plugin, EvoluteTools T.MAP. First of all, I'd like to thank all of our beta users. You provided us with a lot of great feedback, and thanks to you, T.MAP has been getting better. We had many requests for a tutorial video, since the interface is complicated. We've tried to make it as simple as possible, and we're still working on it. But part of the complexity arises from what we're trying to do, a general tool that will handle a wide range of surfaces. The interface will always be somewhat complex, but with a little experience it will get easier. My plan during this tutorial video and the next ones is to start simple before I slowly move on to more complex examples. Today I'll work with a simple closed surface. Closed surfaces are convenient because they don't have any boundaries. Boundary treatment is a hard task to deal with, and we will look at it in the next video. But in this case, the interface of T.MAP is lighter, with only the core options of the plugin. So let's look at this example. There are 3 commands in the T.MAP toolbar, and we'll start with the first one. It's the most important one. So if I select it, it invites me to select an input surface. It can be a NURB surface or a mesh, any type of surface you want to parameterize. Once I select it, I get to the menu. And you can see a lot of options here. So I'm not going to touch the top ones yet. I'm going to look at those 3 bottom ones. Those 3 decide which type of output the command is going to produce and add to the document. So I'm going to select all 3 of them and show them to you. Depending on the size of your mesh, the whole operation can take a while. But you can see all the steps here in the log, and for each of these individual steps, you get a progress bar at the bottom showing you the advancement. Here we go. So we didn't run into problems here, and you can see all the outputs I selected stored in the current layer. So let's look at first the pattern mesh. The pattern mesh was created because I selected the create mesh option, and it's just a mesh layout that follows the new parameterization that the command computed on the input surface. The second type of output are the level sets. This is a network of curves that was computed on the surface and that follow the parameterization. You can see that they correspond to the pattern mesh. And the third type of output is a different mesh. In this case, it looks exactly like the input one, but if you have a NURB surface as input, it's gonna be a different mesh. But it's in this mesh, the texture coordinates corresponding to the parameterization have been stored in the vertices of the mesh. So that's a mesh that's ready to be textured with any type of texture file. We're going to look at that at the end of the video. So let's go back to the start. I'm going to hide this first example and launch the command again. For the remaining examples, I'm just going to select create mesh as output, and it's going to be enough to compare the meshes to show the influence of the input parameters. So if we look at those input parameters, let's look at the first one, the type of mapping. This is probably the most obvious influence. You can choose between a quad pattern, which we used in the first example, or a triangular pattern, which I'm going to try to produce now. So in the case of a quad pattern, you get a mesh with only quadrangular faces with 4 vertices. And obviously in the triangular case, you only get triangles. In both types of mapping, the parameterization is computed so as to minimize as much as possible the distortion between the edges of the output mesh. Here we go. We can look at this outputted triangular mesh and compare it to the quad mesh I produced previously. So the mapping type option is the easy one, and the rest of them are a little more intricate. Let's look at the second one, the directions option. So if we go back to the first example, actually, for a minute, and look at the quad mesh we produced, you can wonder why the mesh is like this, how we chose the directions of the parameterization and of the mesh here, for example. And the answer for this first case is that we didn't, because we chose in the directions field, we chose none, which means that we didn't influence at all the directions and let the command decide for us the way that the layout was going to look like. It's a valid choice if you don't have preferences regarding the directions of the parameterization. Or in the case of a really complex mesh where you can't really control and influence the directions everywhere. Especially in the case of a mesh with a lot of complex boundaries, which we'll look at in the next video. But if you do want to influence the directions, then T.MAP provides you with several options to do so. For example, in the case of this surface, you might want the directions to be aligned with the axis of symmetry of the surface, for example. So we look at the first option that you have with T.MAP, and probably the best one, the one that gives you the most control, is to use curves. So I'm going to select the curves option and launch the command again. After you clicked OK, T.MAP will ask you to select a number of curves that are going to influence the parameterization. In this case, I have created one simple curve. I just created it by intersecting a plane with the surface, and I get this smooth curve along the rough axis of symmetry of the surface. So I'm going to just select this curve and launch the command again. See what comes out. Almost there. All right. So if I look at this pattern mesh that I just got, you'll see that it fits the requirement way better. We can compare it with the one we got in the first example. And here you have no alignment with this axis of symmetry. And in the present case, we have aligned the parameterization way better with the required input curve. So this is a very powerful way to influence the directions. So of course you can use as many curves as you want on the input surface to influence the parameterization. The curves don't even have to be on the surface, they can be around and just roughly describe the directions that you want to achieve. Let's do another example where I'm going to use several curves. I'm going to display again the original surface and say that I want to align the parameterization better with the legs in this area. So I can either use, if the input surface is a NURB surface, I can use Rhino's built-in commands for that in freeform, interpolate on surface, sketch on surface, etc. If your input, like me, is a mesh here, we included another command here that basically does the same, but for meshes inputs. So this third command in the T.MAP toolbar is used to create geodesic polylines on a mesh. For example, here, you just select 2 points on a mesh, and it draws a geodesic curve. All right, so I'm gonna try to launch the command again, align with curves once more. And this time I'm gonna, in addition to this one, I'm gonna use this curve I just created. And we'll compare the results with the previous one. All right. So here is our result. You can see here, it's of course never perfectly aligned. It's trying to fit the constraints as well as possible. But if we compare to the previous results, where in this area we did not follow this requirement at all, we have now a better fit here along the legs. And still, in this case, a good alignment with the axis of symmetry that we defined. So you can see that using curves on the surface is a really powerful way that allows for a lot of control. But it can sometimes be tedious to define all these curves. It requires some work, basically, which is why we included this additional command to help you in the process. Another option for getting the directions is to use the curvature of the surface. So I'm gonna hide the previous example again and launch the command again. So here, if you select the curvature option, you can use the features of the surface to guide the directions. If the surface has enough areas with a strongly defined curvature, the resulting mesh will fit the features better. In case of a quad mesh, for example, the faces will be less distorted and flatter. If you select curvature, it comes with an additional option to influence the results, which is this fixed percentage option. They come together. The fixed percentage parameter indicates what proportion of the initial surface should be used as influence. This is arguably the trickiest parameter. There's no good solution that will work in every case. Some surfaces have well-defined curvature everywhere. Others have large, flat or spherical areas where no direction is better than another. Start with a low number, 10%, for example, and increase it if your goal isn't reached. I will try with 20% in this case. Overall, the big plus of using the curvature as a guide is that it doesn't require any effort. Without defining curves manually, you can still obtain a result that's more coherent than when you select none as directions. Only it should be handled with care, and it will take some experience using T.MAP to really master the curvature as guides. So let's look at the result. Here we go. So without having defined anything on the surface, without any work, we were able to compute a geometrically coherent and smooth parametrization on the surface. I'm going to use the command one last time to show you the last parameter I didn't discuss yet, which is the number of level sets. This one defines how many level sets will be created in each direction. You can think of the level sets as basically the number of curves that you produce when you create curves, which means that the more level sets are created, the closer the curves are to each other. And in terms of the mesh, the smaller the faces of the pattern mesh will be. Let's look at it through an example. So far I've been using 80 level sets. I'm going to switch to 40. And I'm going to create texture coordinates to show you a texture example. Alright, I'm going to use the same curve here. So in this case, half as many level sets will be created, which will result in edges roughly twice as long as in the previous case. We're working on replacing this parameter with an approximate target edge length, or the distance between two parameters, and it would be a lot more intuitive, as some of our beta users have been telling us. But let's look at this example. Here you can see the pattern mesh, and we can compare it with the previous case. As expected, we get a similar mesh, but with bigger faces and edges twice as long, roughly. For this last example, I also created the texture mesh, which looks a lot like the input mesh in this case, but embeds the texture coordinates. So if you want to texture the surface, the command you should use is texture palette. And here you can see a panel where you can load any texture file that you have available and use it to lay out on the mesh. So in this case, we created a quad pattern, so we need to load a quad texture like this one, for example. And once it's loaded here, you can just drag and drop it on the mesh and see it in the rendered view. You can use another one. And that's it for today. Thanks for listening. Don't hesitate to keep giving us feedback or ask for help, either on our Magnet forum section or through our support email address.